Alright, we have the same situation as in lab. However, we're going to look at it energy based now. Alright, so we have the law of conservation of energy. Basically says that all energy is conserved, no energy is lost, it's only just transferred to something else. So if we have a closed system, EI will equal EF. The initial energy will equal the final energy. The ET, that would be either EI or EF, or energy at any point, is equal to the kinetic energy plus the potential energy. The kinetic energy is the energy of motion. Potential energy is from a force acting on it from a distance, or on it, or waiting to act. There's a lot of potential energy in the universe. Anything from molecular bonds to things at a height above a planet, gravity pulling down on it. You let something go, it falls down. Changes potential energy to kinetic energy. So we know that EI in the initial state, before we launched the cart, I forgot to keep this on the thing. EI is all kinetic energy right when the very beginning. Once the spring has been launched and the cart is leaving, there's no potential there. Potential energy then is at the final point, because the cart's not moving at all, but then it starts to roll back down the thing, so there's energy there. So EK equals EP by substituting this into this first equation of EI equals EF. That should be obvious. I'm not going to go into the derivation of these terms. I'll explain them though as best I can without using math that you don't know. EK is equal to 1/2 mv squared. The E potential energy is equal to mgh. That one is easy to explain. Just think about an object being a distance from the Earth. The higher up you hold it, the more potential energy it has. So, using the equations of what EK is, we can find what the energy is from the spring, what the velocity of the object is from the spring. And V equals the square root of K over M XS. You guys should have done K already. If not, I'll write it up at the end, I guess. XS is the spring. That's how far the spring has been compressed. K is your spring constant. M is the mass of the cart. And V is the velocity of the cart after the spring is launched. Getting lost. There it is. The height, what we care about in here is how far it goes up. So when you launch the cart and it goes up, you want to know how far up it goes, how much distance it travels on the ramp. What distance gives us with the angle is height. And if you remember, we have height up here in the potential energy equation. So we solve for height using trigonometry and we get d sine theta. So then going back to the EK equals EP for this situation, we have 1/2 mv squared equals mgh. M on both sides, it cancels automatically. Then we substitute in for V what we know. So we put in that square root of K over M XS and we square it all. That gives you that. And then we put in for H what H is, and that gives us dg sine theta. Then when we solve for theta, we divide by 2GD. That gives us K XS squared over 2GD. Right? And then you take the sine inverse of that. Oh, I meant left to m out. 2 mgd. Miller-Genuine Draft, yeah. To GDM, whatever. And then we take the sine inverse of that, and that gives us theta is equal to sine inverse k xs squared 2gdm. So what I want you guys to do with that is using that k that you had from class and the m from your cart and the d, you should be able to do all this and see what that angle would be. And just report on that from your final task. I believe you have all that information. If not, let me know.